Okay, very good. So, data structures, algorithms, we're going to go through some policy stuff. Most of you have kind of heard or know a little bit about how I do my classes, but I'll go over that stuff again. Apologies if you've heard this about 4 times already from me, but some of us have not had this course before or any of my courses. So, I'll go through that and then we're going to get into some math and coding first day. So, first off, if you don't know me, you can call me Jeff or Professor Yates or Mr. Yates, however you prefer. I really love coding. I started in high school, like some of you have, and that was pretty early days. And really got excited about computer graphics. I worked in the game industry and in the software industry for 20, 25 years, and really enjoyed it. As most things do, I got into management and love that too, but I've enjoyed getting back into coding in the last 10 years and been doing 6 of it here at College of Marin. So my perspective is always, how do I get you a job? Now, I know everybody here is still on their journey through school, but my experience is hiring software engineers and building software products. So hopefully I can give you a little sense of what at least it was like when I was in the job market for about 20 years, and most of that was in the Bay Area. And I'll kind of give you that perspective. I think of you as my senior students now. You're not in beginning programming anymore, so I'm going to give you a little more responsibility. My expectations of you on an sort of an integrity level automatically go up. I think of you as my more experienced employees, if you may, and I want to trust you, and we want to work together to build great things. So that's a little bit of my perspective. Appreciate you being here. I appreciate you taking the course. We'll talk about all the detaily stuff coming up. The way I kind of like to teach, maybe you've heard me give this kind of speech before, is I won't try to make you paddle. So if you're in this class, I assume you want to be here. I'll try to lead you along the way, give you everything you need. I'll always make myself available, but I do expect you to kind of try to do the work. Um, yeah, that's pretty much how life is going to be for you going forward. Okay. All right. Great. Thank you for that. Okay. So let's kind of jump into the course because we got some material to cover. So our objectives are to really start thinking more critically about data structures and algorithms. We've all had some experience writing code right down at the nuts and bolts level, and we'll be doing some of that for sure. But we want to elevate our thinking in this class, and in particular in this current age with AI, we are going to all be challenged to be useful, to be thinking at a higher level. And that's really going to be more at the abstract kind of level. It's about how do we want to organize our data and code, and what is the most efficient way to tackle some interesting problem. So in this class, we're going to study famous problems, which I can tell you, and you won't be surprised, that every single one of the things we're going to study this semester have been solved a million times and ChatGPT and everything can solve it in its sleep. It can answer every question that I can throw at it or you can throw at it. So it's real easy to get the answers. Hopefully, we can have a journey where we expand our thinking. And it is my job, for better or worse, to also assess your level of understanding. So hopefully, it's fun. I kind of think of it as learning card tricks. If you've ever had somebody teach you a card trick, they're like, okay, do these exact steps and do it this way, and people will be amazed. And after you learn it, it's kind of like the magic is gone. It's like, okay, it's just a bunch of steps. But you see people kind of respond and they go, wow, how did you do that? Right? So algorithms are a little bit like that, especially the famous ones. There's really only a couple ways to do it exactly fast and correct. And once you know it, it's kind of solved, right? And so some of the most famous algorithms have been solved, and they are named after some very famous people. Some algorithms are named after the approach that the people took. Some are named after the people, and this causes a lot of confusion. So we're going to be throwing around a lot of famous names and words. It gets a little bit hard to follow. The key point is we're learning kind of special ways to solve some of these puzzles. Now, many of these puzzles that we're going to solve can be solved in multiple ways, because sometimes if we have a lot of memory, we can do things very fast. It's kind of like having scratch paper during a final exam or no scratch paper. If you got a lot of room or a whiteboard where you can write stuff all over the place, you can tackle the problem a little differently than if you don't have a lot of scratch paper. So because of that kind of trade-off and other similar kinds of trade-offs, there's more than one way to solve some famous problems. It's like, hey, do you want to do it fast, or do you want to do it with very little memory or some balance in between? These monster machines on our desk have tons of memory and tons of computing power. They have something like 12 CPUs in there. So they can do a lot of number crunching. But if you have a little Arduino in a drone or some robot on Mars that doesn't have a lot of battery power because of its solar panels, then you do not want to be wasting a lot of cycles. So you got to choose the right solution depending on the situation, okay? So that's the other part of this class we'll sort of try to introduce you to. And of course, we're going to be working mostly with these computers, but I do have some cool Arduinos that I'm going to see if I can hand out to you guys this semester so we can try doing an algorithm in a smaller space. That's when we start to really realize that we've got it good with these monster machines. They can crunch through stuff, and we may have no idea how inefficient our code is because they're so insanely fast. So we'll try to introduce you to that. And then we need to introduce, and this is the real thing that throws most people, and certainly it messed me up when I took this course in a class full of 500 people. We need to start to learn how to talk about this in terminology so that if you go get a job or you're talking with another student or you're taking another class, you're using the same language that people generally use to talk about, and to be quite honest with you, to sound like you know what you're talking about when it comes to algorithms. There's a fairly standard language that we use to talk about whether something's fast or slow, or really, to put it more precisely, how much worse do things get as the problem grows bigger and bigger? We can all sort three cards that I deal out in front of you on the table. But what if I deal out a million cards on the table, right? So suddenly your strategy for sorting might really need to change. It might have gotten much worse, and maybe got so bad so fast you just can't do it. So we need to introduce that language and begin to get a little bit mathy and incorporate some math into this discussion. We'll try to keep it at a minimum, but there's no avoiding the math in this particular class. Now, that's really kind of the performance side of things. There's also the data structure and the kind of higher level, let's just call it object-oriented description of the problem. So take a puzzle, right? We have something called a piece. What is a piece? Well, a piece of a puzzle has four edges and they sort of fit together uniquely with some, maybe only one other piece in the puzzle, right? So how do we model that in an abstract way without getting too detailed about the actual implementation? In other words, do I need an array or do I need like maybe a string? I don't know. But I know I have this thing called a piece, and then I know there's this bigger thing called a puzzle. Okay. So that's what we mean by abstract data types or ADTs. Describe the problem in general terms, and then we'll start putting that into code and filling in the guts. So we'll start using these terms gradually as we go through the course. And the more examples you get, probably the more comfortable you'll get knowing the difference between these two things. So, high level, we're going to kind of have a survey of a whole bunch of famous algorithms. There's no getting around it. This kind of course, we are required to cover the same kinds of things that every introductory algorithms course covers. Can be a little boring sometimes, so I'll try to mix things up and give you a little more entertainment on this. But it really is what I would call a survey course. We're going to go look at different card tricks. Here's another one. Here's another one. And you'll be like, whoa, like, how do you expect me to memorize all this stuff? Well, I don't, right? There's no way we should all memorize all these things. What we want you to do is see a lot of examples where you're like, oh, I'm starting to kind of see the idea here, right? What are the little tricks? And eventually in time, you'll be like, oh, yeah, I know this really awesome algorithm that would really be perfect for this particular problem. That's why people get hired for software engineering jobs. They go to an interview and they answer a lot of questions. They like, hey, I'm going to give you a string of characters, the alphabet. How do you reverse that? Get up on the whiteboard and explain to me how you would reverse that in code, just generally speaking, right? So if you can articulate really interesting and unique ways, and importantly, you can have a sane dialogue about that, people will look at you and say, I like this person. I like the way they think. I think they're going to fit into the team here. Okay. So algorithms are really kind of the place that we want to take our brains in terms of a career as we go further along the line. Now, if you're just going to be working in STEM and doing something, let's say with Python or even with C++, reloading some data and putting it in a different format in a spreadsheet, you're probably not going to need algorithms every day. Okay. So really, this is the dividing line career wise where you're getting into a more serious kind of software development culture. Okay. And if this is not for you, that's totally fine. Many of you, obviously, you just, you need to take these courses until more specifically what you're doing. But that's really where this course ultimately leads you. Solving some of these problems and, going through the specific steps and choosing the right data structure that actually helps that algorithm work well. Okay. So we're going to cover stuff like sorting pretty quickly. We're going to spend about 2 weeks on sorting. Believe it or not, there's a lot of different ways to sort stuff. And there are a lot of trade-offs and a lot of side effects based on how we actually decide to sort some stuff. So I'm going to have a deck of cards for everybody probably next week. And we're going to be just dealing some cards out on the table because some of these things are like card tricks. The steps to do them are kind of not intuitive. So before we write the code, it's helpful to have a physical experience with the algorithm. So we'll kind of do that. Then we're going to review our basic data structures, growing from arrays, which hopefully most of you are pretty familiar with, up into these abstract ideas like stacks and queues. So stacks are a lot like those plates at the buffet that stack and there's a spring and they just get pushed down, right? So how do we build something like that in code? And linked lists, something hopefully everyone's introduced to. We'll go over those again. Then the really bigger stuff, searching through binary trees. How does the computer quickly figure out if there's a particular word in a dictionary of 150,000 words? We're going to be working with some very, very large dictionaries of words. And if we're going to just search them from the beginning to end, it's going to eventually start slowing down. So can we build a structure like a tree that actually allows us to find things much, much faster? And how fast would that actually be based on the shape of that tree? So those are all the interesting questions, and there are some very interesting strategies and data structures that'll let us do that. Then we get to something that is not a tree, something that's not uniform, something like all the roads between here and New York. That's like a graph structure. And there is probably an infinite number of ways that we could get to New York if we really didn't care about the shortest path. So, graph theory and graph research goes way back and realistically is a math in and of itself and doesn't really necessarily even require code. But the fun thing about code is we can actually implement this math and see the results and actually do some pretty interesting things. So we will spend a little time on graph theory, writing some somewhat gnarly code, to be really honest with you. A lot of this code will have been written for you, and you'll just need to fill in some missing pieces. Again, these are all solved problems, so I want to kind of bring you along. I don't want to dump everything on you and say, here, go write this, because all of these things are out on the internet already. All of these algorithms are quite famous. So we'll introduce you to these ideas. Then we'll look at strings. Searching for words so you can edit something in a really large document is something we all take for granted. When you say Control F to find something, how does it actually find something in War and Peace, and find all of the things that match the pattern that you're looking for? So those are really specific string-based algorithms. And you might think, well, why is that any different than just searching? Well, in our English language, at least, we know what the letters are. And there's not an infinite number of letters like there's an infinite number of numbers. So there are tricks that we can play that allow us to maybe go even faster when we know we're searching in a character set of only, let's say, 180 characters at most. So those characters could include characters from other languages like kanji, for example, right? But we still are only having to deal with maybe 100, 200, 300 of these individual things. So strings and the algorithms associated with strings can be optimized so that we can have unique and in some cases very famous kinds of algorithms. There's one famous story of a researcher and professor who forgot the canonical or the way this person was taught on the way to lecture and actually invented one of the more famous improvements on that particular algorithm and taught it to their class. And then it became known as one of the things we use in editors today when we're searching for text. So there are still amazing discoveries happening. In fact, we'll see that in this graph category, this actually happened during COVID. While I was teaching and saying, yeah, no one's fixed this problem for 50 years, right? 4 students in Japan during COVID cracked it and came up with a brand new way that just blew away everybody, right? Been searching for an answer for 50 years. So these things still actually are getting faster over time. It's kind of hard to believe, but they're still actually improving slowly. Okay. So, number of things we'll go through. We can't cover them all. There are way more algorithms out there than we could possibly cover. But the reason we want to cover them is because when you go out there and you use things like Python or libraries, or you use software from companies like Autodesk or Google, or you play a video game, you are engaging with seriously optimized algorithms, especially in video games. And especially when you watch a movie like Pixar, they are really using some very highly optimized algorithms for their particular solutions. And so if we want to be coders, it really is the ultimate game to be able to engage in some of these algorithms. And one of the most fundamental ones is sorting. I say it all the time. If you're going to do anything, the first thing you pretty much need to do with it is sort it, and then you can move on from there. So if you have stuff flying at you in a video game and you don't want to see the things further away than the things that are closer to you, we need to sort them in the order of distance to the camera. That stuff is happening at 60 frames a second, and there are lots of ways to do it, but that's one of the reasons we might need to use sorting, and it happens really, really fast and all the time. Okay. So if you get the algorithm right at a very large scale, it can mean the difference between solving it in a few seconds and never solving it in our lifetime. And we will study the difference in that here pretty quickly. You'll see why just a little bit of a fix can turn something into in our lifetime versus never, right? Or not viable. Okay. So there's a lot of algorithms out there. They're all integrally intertwined with the way that we store the data. We'll study some of them in this class, but there's just a lot that we won't actually end up covering. So we're kind of here down at the bottom. If you ever want to follow along with these slides, you can kind of just click into the PDF in Canvas. Many of you probably know that. I'll always have them posted in our Canvas before class starts. But if you click into this Wikipedia here, you'll kind of see there are a lot of algorithms, man. And you'll see stuff that's, Kruskal's, Prims. We're going to cover these things, right? But there's just no way. It goes on and on and on, which I know is daunting. But, you specialize in a particular area, maybe graph theory, maybe sorting, maybe graphics types algorithms that are actually useful for a game company that you're working at. Okay, so you don't need to know all of them, but the ones at the bottom, like sorting, searching, hashing, recursion, and the fundamental data structures, those are the ones that we all want to know. And that's why, we're kind of required to learn them when we take these classes. Okay. So just a little broad sketch of things. And interestingly, you should know that algorithms go way back. So well before the computer existed, what did people have to do without television? They just sat around and solved interesting math problems. So this one, the Sieve of Erastusthenes, 200 BC, right? So thousands of years ago, pick two, create and mark all of its multiples, then mark all of the multiples of 3, 4, etc. And if you get anything that's unmarked, that's a prime number, okay? So people were imagining these things well before we had computers, okay? So that's a pretty old one. Another one that often, unfortunately, gets forgotten, and by me, of course. And I'm glad somebody brought this to my attention. Ada Lovelace is recognized as one of the first designers of a numerical methods algorithm in around 1843, before computers were invented. And it was a set of steps for calculating one of the Bernoulli numbers. Okay. So this is really widely recognized as one of the first algorithms that anticipated the building of a computer, okay? But in the 1930s, around World War II, there was a need to crack the encryption codes that were being used to transmit, between the warring parties. And so there was a motivation to build a machine that could actually solve these. And Turing and Church were some of the people who worked on that in the early days. So in a sense, algorithms for computers are not that old. The stuff that we're going to talk about will have names of people from the 1950s and 60s. And they got lucky. They, figured it out before anybody else did. Maybe they had a computer so they could try it out. Nowadays, new algorithms are being invented by the hundreds or thousands every year, depending on the problem. Okay. And it's kind of hard to keep track of them all. Now, here's another thing I would like to point out that I really like about computers. I liked math, but I really struggle with it sometimes when it got really intense, right? Like we all do. So mathematical analysis can go very far at solving very important and very hard problems exactly by using equations, right? Symbolic math, an incredibly powerful thing, right? But certain things, we don't need to know the exact answers. We want computational methods to go find or approximate the answer within a certain precision, right? So if I want to find out if something's 0, I'm okay if it's 0.00000001, right? That's close enough for me. So if I can design an algorithm that eventually finds the answer after looping and looping, that's good enough. That's called numerical methods, and there are many, many good numerical methods algorithms for finding solutions that are close enough. Driverless cars, probably one example. They don't know exactly where you're going to be while you're crossing the street, but they can estimate it, and every 60th of a second update their guess of where you're going to be in another 60th of a second. So these are other important examples of algorithms, okay? And so computational analysis allows us, with very fast computers and clever algorithms, to be close enough for what we need, okay? So again, it depends on the context and the situation, but there are a lot of fascinating problems for solving this. So a lot of global illumination models, for those of you who are interested about in physics, heat transfer of heat radiating off the walls is really quite similar to light bouncing off the walls. If I have orange sunlight coming through on this wall and it hits that wall, it's going to bounce a little bit of orange onto the other wall. And that's going to bounce and that's going to bounce. So in computer graphics, global illumination is an iterative algorithm that calculates all the bounces of light and then eventually paints us a 3D synthetic picture that looks realistic because we've had a model for how we think light more or less works. It's not exactly correct, but it's a computational approach that has famous algorithms developed to actually solve those problems. Okay. So network theory, of course, can apply to roads between here and New York, or it could be connectedness in the internet. Where is somebody able to attack the internet and take down a major node to cause the most amount of harm? Or a shipping port, or a train depot, right? So during World War II, people were analyzing these things pretty carefully to figure out where can we knock out a train to maybe stop some supply of weapons, etc. Okay. So we will look at length in this network connectivity problem where we have nodes, right? Little points of connection and arrows that travel between those things. Okay. Uh, so we're going to try to get the correct answer, and we're going to try to understand not only how we got it, but what is the cost of getting that answer as the complexity of the problem grows. So if I gave you a deck of 5 cards, we would say n, or in this case, x is equal to 5. And I would say, well, how long is it going to take you to sort 5 cards? Okay. So you might have an algorithm that, grows in cost in a flat line way as the number of cards increase. So it doesn't seem so bad. Linear is not terrible, right? But if you said, oh, yeah, the more cards you give me, it's actually going to get slower by 2 to the x, whatever the number of cards is. So that is a very aggressive sloping green curve, and things are going to get slower very fast, right? So you might be looking like you're just as fast as someone with a linear approach, but all of a sudden we get past 9 and you start to hockey stick up, okay? So these equations, either a linear 50x, so that 50 could be a 5, a 50, a 10. It's still a straight flat line if we remember our math, right? It's rise over run. So we call that a linear growth in how much slower it's going to get for you to solve a particular problem. So in terms of computer scientists, we would say, oh, the performance on that algorithm is linear. So it's going to get worse, but it's going to get worse gradually and in a predictable way. If it's something like x to the third, we call that, well, the quadratic, or in this case, cubic, right? We raise to the third power. So there's all these names we're going to start throwing around that describe how much worse it's going to get as the problem gets more complex. We're not specifically talking about the exact amount of time. We're more interested in how does the algorithm degrade. Okay, so that's the really first big idea here. It's like, okay, time is not really specifically what we care about because, we can all just get a faster computer. What happens when the problem doubles and doubles again and doubles again? How much slower is that going to get? So we will get familiar with this terminology of performance degradation, and we're going to borrow from some basic math terminology that many of you are probably familiar with already. Okay. So for our horizontal axis, we will normally deal with what I'll call n. How many things? N in this class is going to be like x. It's like how many things are we working with? If I'm sorting numbers of students at College of Marin, n is going to be in the thousands. If I'm sorting numbers of words in a dictionary, that's going to be in the hundreds of thousands. So n is going to be for us pretty universally that horizontal axis. And the vertical axis very often might be time, but it also might be, hey, how many times did you have to compare 2 cards to each other when you were sorting them? So if I were to say you can sort these 50 cards, but every time you compare two cards, I want you to write a little mark on the board. So in that case, I'm asking you specifically to write a graph of your comparisons as the number of n gets bigger. Okay. So we could be thinking about time on the vertical axis or comparisons or many other things. And we'll kind of have an opportunity to kind of see how those things play out in different kinds of algorithms that we study. Okay. But the key takeaway for this course, aside from all the code and all the interesting outcome, is these graphs. Maybe we don't like math so much, but it's not as complicated as you actually might think. Okay. So the terminology for these things are linear, right? The red line, cubic, raised to the third power, or in the case of the 2 to the x, that's going to be exponential. So your people saying it's growing exponentially. Of course, it's not always growing exponentially. It's just a nice word. But if it's something, something to the power of x as x gets bigger, that's truly exponential. Okay. Quick questions on any of that stuff? Okay. All right. So let's talk about languages. So, of course, we can use a lot of solutions that are already out there. Very famous problems need very famous solutions. One of probably the most elegant ones that people use and don't even realize it are Python dictionaries. Python dictionaries are and sets are super optimized, very easy to use in code, and you probably don't even realize how much technology you're using there. We're going to build all that stuff from scratch in this class, even though you'll probably go right out and use the libraries that are already provided after we're done with this class. That's just kind of what we got to do, right? So once you get out into the real world, you're probably not build everything from scratch, but there are situations where you might want to do it. When you use these things, they are generally very standard and optimized, and you know they don't have bugs. They might be complicated. We're going to see in C++ that things can get complicated when we use, different libraries that we download. Maybe we don't need all those special features. Um, if we build our stuff from scratch, as long as we debug it, it's simpler. We own all the code. So there are reasons for doing it. But admittedly, very often today, we just download a library and it works. But in this class in particular, we're just going to be working with arrays and building things on top of arrays. So we're starting from the very, very bottom. And that should help make things a little easier for Java programmers who are joining us and maybe some of our Python folks as well. So we're going to keep it simple. We're going to have a minimum number of libraries that we're using just so we can really understand all of the foundational stuff that we're working on, okay? And we're going to try to build all our own stuff. We'll be using C++. I think all the stuff that we're using is pretty basic, but I'm going to take some time here to introduce some basic concepts you're going to need right away, and then we'll dive into our lab. So we'll get you out of here before you run out of time in this class today for sure. So, and don't worry, I will go over pointers with you several times because as the course goes on, you're going to need to be able to understand how to work with pointers in C++, but I'll help you with that. Now, if you are only Python coder, just make sure you let me know that. You don't have to do it now. You can come around some other time, but I want to just be aware of who's who because there's a few more challenges there for you in some of the stuff that we'll be doing, okay? Questions before we press on? Okay. All right. I won't beat you over the head with this one, but again, I consider you to be my senior students. I have a lot to grade, so I appreciate that everyone's going to take this class seriously. Usually I see these challenges more in the earlier classes. It's not a really huge class, thankfully, so I've got a little breathing room, but I do hope that you'll take it seriously. I think we'll have a lot of fun doing it. And fortunately for you, there's not a long waiting list of people trying to get in this semester. We will be using these slides. So everything you need is in these slides. I'm going to put a lot of coding examples this year in programiz.com. I have used Replit in the past, but Replit's business model has changed dramatically. For those of you who know it and like it and are paying for it, you're welcome to keep using it. I just don't want to have you have to pay any money for this course. You're also very welcome to use your own integrated development environment, VS Code or something else. And probably I'll just ask you to upload a text file, but I'm going to be giving you a lot of pre-written code. So you'll need to, if you're using your own system, you're going to need to download that stuff every time and then modify it and then send it back up again. So I'm still in the process of converting things over. So bear with me, but I think for this week, things are pretty straightforward for you. Okay. So Program IZ for all of our programming samples will be pretty easy. We don't have to log in for a lot of our simple programming examples. But once we start reading and writing files, then we'll probably switch over to what's called Program IZ Pro for the larger assignments. Okay. So we'll come back to this stuff. I don't want to bury you in all the caveats here, but you can basically trust that, if you feel like you want to check out Program IZ Pro, I can get everyone full licenses so you don't have to pay anything. Generally speaking, you don't have to pay anything anyway, but we have a special relationship with the company and they're actually listening specifically to your feedback. So they have changed their product strategy in a really exciting way based on the feedback from everybody in these classes. So you have a direct line to this company through me if you have some feedback about the product. So we will be, of course, working from our Canvas course. I think this link is probably a little out of date. We will also be using Quizlet to help you study because there's a little bit of memorization in this course. So you might want to try to get a Quizlet account if you don't have one. We'll be using Program IZ. And also there's a cool site called visualalgo.net that has a graphical representation of a lot of really interesting algorithms that we'll talk about. Increasingly, Program IZ has these things kind of improved, so we'll see some of them there as well. If you're curious about CPP or C++ in general, CPP reference, most of you know about this. Geeks for Geeks is out there, W3 Schools. There's all sorts of really useful things. And Desmos. Many of us know Desmos. I'm going to bring it up a few times because we're going to be talking about these curves, especially for homework 1. So you may find Desmos to be useful to get familiar with the shape of some of these basic curves that we're going to be using. This is my favorite book. It's written in Java. I like it. It's been out for a while. It might be, I don't know if it's out of print. You can still get it. I don't think they're updating it, but it's a very accessible book. It talks about the algorithms, and I follow it pretty closely, even though we use C++ in this course. So you might find it good. There's also an online free Coursera course if you ever just need to hear it from a different source. So lots of information out there if you want it. The other one that is more of a reference book, but is probably a little more popular, and it's very big, is this what's called the CLRS. That's the initials of the author's book. Okay, CLRS is very comprehensive and covers most of the base algorithms. So if you like books, these are two useful things to have on your shelf, but you don't actually have to have them. Okay, so let's talk about Program is Pro. So Pro, even though it says Pro is free, if you log in and create an account, you can create up to 5 different projects. And once I upgrade you, you can create an unlimited number of projects. And at the end of this semester, at some point, I'll need to downgrade you, but you can still always download zip files of those projects to some other system. And, for the most part, I've left everybody in the class who's still a continuing student. So it's kind of a nice thing to be able to use if you're interested in doing something in the cloud like that. You can also, like I said, if you're already on Replit, you can use that, but you can easily bring your stuff over directly from Replit into this system. If you want, just let me know and I'll help you understand that. So let's take a look at one thing real quick. For those of you who haven't seen this, go to your web browser, type in program is online compiler CPP or something like that. So this is going to take you to this URL. If you're following along, you can also just click on this URL right here. And I just want to really quickly show you this. Many of you who've had my other classes have probably seen it. But this is going to allow you to make a change to code in C++. So if you've not done C++ before, this is a real quick introduction. So, so here I've got things zoomed up. So I'm going to zoom out in my browser, and you'll see pretty quickly we're going to get some ads popping around here. This is the free online compiler. No login is needed. I can run a program, right? I can change the program. So we're just using the comment out right there, right? I can run it again. And if I want to capture this forever, in quotes, just click on share, right? I just clicked on share, and now I have a URL that will not go away. So this is a persistent URL. There's no name associated with this. It's not public, but now you have an asset in the cloud. And as long as you remember that URL, you can always get back to that code. So this is what we'll use for small practice problems. And if you want, you can use this for your labs. So you can do your lab work right here. Just, when you're ready to submit it, share the code. Or if you want to save it and come back later, share the code and come back and modify it again and then reshare it, right? So here's my new link, right? It's got hi there, okay? But if I refresh at this link right here, I'm going to lose my hi there, right? But the hi there version is still there. It's just got that link that we just copied. Okay, so if I go to that other link, there's my asset. So it's a little bit quirky. It's a little different than saving a document. But if I wanted to say, hi, Jeff, I need to now share it again. And I'm going to get a different URL. And you might think, where do these things go? Well, they're going in a database somewhere, and they pretty much hang around. Okay, so as long as you can keep track of your different URLs, right? So here's the hi there, and here's the hi Jeff URL. We can get back to our assets. So this provides us a quick and dirty way to do some quick work, submit some labs, and it's not a bad way to go. You can still upload your own text file, but I just want to explain this sharing idea for you since it's kind of, convenient for the easy stuff, okay? Questions on that before we move ahead? And there's some features here. You can probably see we've got different languages. So you can jump into Python, you can jump into C, you can jump into R, like many of these hosted languages online, okay? It's just
like link to our account.
No, this is actually completely anonymous. So if you lose that URL, you've lost your work, right? But if you submit it in Canvas, for example, you and I are the only people who know about it, right? And you can always go back in Canvas and pull that back up again. And it runs on your phone and everything else. So it's a tool if you can find a way to use it. And I will probably use it for a lot of one-off things until things start to get really complicated. Okay. Okay, so that's that. And just notice that, you can dial in a different programming language relatively easily with your URL here. You can change to Python or Java or something like that, okay? Now, I think this is from my beginning class. So we all know if we forget to put a semicolon in there, we're going to get a compiler error. So, feel free to experiment if you're relatively rusty with C++, just to remind yourself of that. I will probably make those mistakes as I go. Now, for bigger projects, which will be coming, we're going to need a bigger solution, a bigger tool. That quick online thing is not going to work. So we're either going to need to get you guys into Program IZ Pro or some other system. So I'll support you with whatever you choose, but I'm going to try to focus on the algorithms part of the course and not supporting too many other systems. So I'll probably give you the code in programiz.pro projects. You can download it and then go from there, right? Or you can just use Program IZ Pro if you want. So just think about it, take a look at it. If you sign up for it, just let me know what your account email is, and I will give you like expanded permissions, okay? For starters, you can do 5 projects in there anyway, so it's not like there's an urgent need for me to expand, but I'm very happy to add you to the course so you can get extra access to stuff, okay? And they do have a full Data Structures Algorithms course online, and they got some cool visualizations of some algorithms. So you may find it to be a very interesting course in any case to actually work with in tandem to the stuff that we're going over. Okay. Quick word about Canvas structure. Everybody's probably seen the welcome module. I will not go through that again because many of you have had my courses. So starting at home, right? Every week we're going to have a lecture. You can click on that lecture and follow along, and that will provide you some crucial links that you're going to need to do quick practice problems. So that's probably the easiest way to get access to the links. But you can also, use the practice problem pages in the middle here, right? Those are just sort of the exact same links that are in the PowerPoints if you want for a particular lecture. And then our labs are there. So there's our lab today. We'll talk about that here in a second. And then our next lecture, 2 lectures per week, of course, and the process repeats. And we have our lab number 2, and then we have due in 2 weeks, quiz 1, and due in 2 weeks, homework 1. Okay. And that cycle repeats in kind of chunks of four lectures. Okay. So the idea with the quizzes, again, for new folks, you can take it 3 times and I will keep your highest score. Questions are randomized from a large pool of similar questions. So you won't always get the same question, but it'll be the same kind of question. And then you will, submit that. And you'll have 45 minutes for each one of these. Typically, they take anywhere from 20 to 30 minutes, depending on how closely you've been following stuff. So should not take you more than 45 minutes a week if you try it once, and maybe even that if you try it 2 or 3 times. Okay. Homework problems are a little bit meatier. We're going to get into some pretty chunky problems. So I'll help you when we get there, but you're going to probably need to spend some days on your 2-week homework assignments. So we'll try to, get them to you 2 weeks ahead of time so you know what's coming and get you the material you need pretty quickly so you can kind of start thinking about it and maybe start writing some code as soon as possible. So that's kind of how things are laid out. We don't have any practice problems today, but we will go through some practice problems. Actually, we do have, well, maybe we have some practice problems today, but we have more practice problems coming up in lecture 2 and beyond. Okay. So click on lecture 1 if you're not already there, and you'll kind of see the PowerPoint, and you can just scroll through it or download it. Either one. It's yours to keep if you want. We've got 2 labs this week. The first lab is probably harder than anybody wants. It's okay if you don't figure it out. It's just a good way to warm up our brains. Lab 2 is a little bit easier. So lab 1, take a look at it. We'll talk about it here in a minute. It's to kind of remind you what recursion's about. We'll kind of see it's an interesting problem. Some of you might enjoy it, but it's a good one, if nothing else, to kind of get your brain going again. And then we'll talk about our homework on Thursday when we come back. Okay. For the most part, these are easier points than stuff coming on later in the semester. So try to jump on the stuff. Quick word about attendance. I do not grade attendance. You do need to be here. It's not an online course. So if you miss more than half the lectures at any given time, I'll probably give you one warning and then I got to drop you from the course. Okay. So please do plan on coming. You, of course, have to be here for the midterm and the final exam in person. We will always have that test in person unless there's a fire or an earthquake or a flood, which we seem to have had every other year. Consider our lab period to be kind of like group office hours. You are welcome to consult with your peers on your labs, especially for today. So you're more than welcome to strategize about the labs. Homeworks, I would like everybody to kind of challenge themselves a little more singularly, but we can talk more about that as we get further into the course. Okay. Attendance, again, I do not grade you on attendance. I do not require you to be here for lab. So, use that time wisely. And again, I will have to drop you if you're not here half the time, right? So any 6 rolling lectures over a 3-week period where you're kind of basically barely here, I'll give you one warning and then I got to drop you from the course. So please or reach out, right, if something bad happens. Okay, so if you haven't done this yet today, please help me out. Go to your Canvas, go to quizzes, go all the way to the bottom where it says surveys. All right, so there's a survey. Let me get this thing out of the way here. Surveys. There's where is it? Attendance. My animation's out of place here. Sorry. There it is. So click on that. Just type in lecture 1 for today. Okay, this is my way of recording your presence in class. It's sort of filtered through our internet IP, so it basically lets me know that you were here and not at home when you do this. If you miss a lecture, that's okay. Just leave it off. If you forgot to do it, but you were here, then it's an honor system. Next time you come in, then put that number in there. I appreciate you helping me with that. Just gives me a record that I can, bring up if we need to talk about attendance. Okay. So try to do that and we'll kind of move on. Please focus on Canvas email. I will be very responsive, but I don't keep up with Outlook. So if you send me Outlook email, it's going to get a little bit hard. So please try to focus on Canvas. I know it's a pain to log into Canvas sometimes from home, but we all got to do it. So please do that. And please read Canvas for your homework. I think you'll find that to be really useful. Very often I will respond to you on your homework through the Canvas assignment system. Many of you have probably seen me do that before or have other teachers that do that. So I'll keep doing that. We have Zoom, but it's just for Friday one-on-one. So for people who want to jump on a call Friday morning to go over something, I will make myself available. I'll even try to do that at other times during the week, but my schedule is pretty packed. So you can guarantee if you come an hour before this class every Tuesday, like today, I will be here in my office upstairs on the 3rd floor. That's my office hours for you guys. But I will also do whatever I can do to help you. If you just drop by my office, I'll always try to say yes if I can. But otherwise, we can set up a one-on-one on Zoom, and hopefully that'll help you out. Okay. So please don't share our link with anybody outside of class. It's private to us. It's in our syllabus page if you need to go find out about it. Okay. Okay, grades. Many of you know this. Quizzes build into midterms and finals. So your quizzes are very formative. The more quizzes you try, the more questions from the final and the midterm you will have seen. So you may find that to be helpful. It's like a little reward for spending more time. Some of us will get that stuff right off the bat, and we don't need to try the quiz 3 times. But if you do, there's a benefit built in. You'll be more prepared for your final exam. Okay. Labs, feed the homework, and I'll try to make all that stuff make sense. But there's our percentages. And remember that we drop one of our homeworks. So out of the 8 homeworks, I will drop your lowest grade. I'm really only going to grade 20 labs. So I'll be dropping a bunch of labs as your lowest labs. You really only need 20 good labs for the semester. Okay. So even though we got like 30 lectures, really it's going to work out. There's about 20 of those that you want to really focus on. So you'll have lots of chances to go back and kind of have an optional lab to improve your lab score. We have 8 quizzes, but 2 of them are just warm-up quizzes before the midterm and the final exam. So there's really only 6 graded quizzes and then the midterm. And that's the course, right? That's exactly and only how you earn points in the course. Okay. Okay, sorry, I know that stuff's terribly dry. So we do have a late policy on homeworks. So you can take 10% a day. So if you turn in something that's totally busted on Tuesday and you would have got a 50% because it was really busted and you turn it in the next day and it's perfect, you'll get a 90% on the next day. Okay. So every day we take off 10%. So you can improve your score quite a bit if you just need that extra day. Okay. So if you if you push it till the weekend, you're not going to obviously be able to really get a very good grade in the class that way. So please try to stay on top of things if you can. Okay. And I think I talked about this. You can use a text file and any IDE you want. Here's our late policy. Kind of whoops. So basically after 5 days, I have to cut you off. So if you don't have it done by Sunday, kind of it's going to end up being a 0. Okay. So try to watch out for that. Quizzes, 10%. I think we talked about this. 45 minutes, 3 tries. It's up to you. You can work out of class. It's open book. You can ask ChatGPT for advice, etc. But please try to work on them by yourself in preparation for your midterm and final exam. And then, of course, the midterm and final exam. I probably have these dates wrong. I got to go check this again. So apologies if these dates are a little out of whack. They change them every year on us. Okay. So, but these are what our tests will be. Open book means you can search the internet. Okay. Now I know there's a gray area now that Google search uses AI. So if you say, if you type in one of the exam questions into the Google search, thing, it's starting to get a little difficult to be a teacher these days. So got to rely on you guys to try to invest in your own intellects. So try to follow the spirit of the rule. Ask for information, not answers. I'll remind you of this when we get a little bit closer to these exams. But both of them are really pretty much the same. And you will get a practice exam a week or the weekend before. So you'll even get a chance to do a practice exam with different questions if you want to. So lots and lots of chances to kind of see what I'm hoping to get from you on these things. Okay. So final exam, midterm, pretty much the same kind of strategy there. Okay. Okay, and labs, as I said, 20 of these. You can collaborate, you can consult with AI. These are the kind of just, formative things that help you kind of build up your skills. Okay. Sorry, one more slide on AI. Basically, it's tricky, getting trickier all the time. Please don't use AI full on during the exams to type in your questions and get answers. That's pretty clearly out of bounds. Okay. So we're trying to assess your level of understanding, even in an open book scenario. Okay. So please try to stay away from that. You can use AI to improve your understanding of key concepts at any time, including on your quizzes and your labs. Okay. But if you find yourself taking answers from the AI or other people, and that has happened in this class, unfortunately, to my great dismay, I received homework that was identical from 3 or 4 or 5 people. That was really frustrating. Basically, that means I failed, I made it too hard, or I didn't give you the right content. So let's hope if you get to that point, reach out to me and tell me, I don't know what you're talking about. Okay. So hopefully we don't have to go down that path. Okay. Just ask for help and I'll try to give it. Okay. If you're kind of like, yeah, I used AI, I'm like, okay, I have to give you 0 for that. So let's not do that. Okay. We'll stay away from that. So great examples. Hey, ChatGPT, what's an algorithm that I could use to do X? Or why is such and such an algorithm better than something else? I am not kidding you when I say I go home after this class and I cook and I have the phone on the table with ChatGPT on and I have conversations about algorithms with it. It blows my mind. And it's fascinating, right? And I encourage all of you to think about trying that out and checking its answers. But very often, algorithms is one of its sweet spots. It's like you're like, hey, I got this problem I'm trying to solve, and I really am not sure what's the best approach. What do you think? It's pretty amazing. So those kind of things engage our minds, and especially when it's a conversation. Obviously, just feeding it a homework assignment and saying, please do this for me, would rather you don't do that. So please invest in your own intellect on that. And I think you'll be in pretty good shape all around. Okay. Questions on policy for AI and otherwise? Okay. Thanks for putting up with all that. I think you know our dates and times. An hour before class on Tuesday, uh, in my office upstairs. Probably not down here next door. I think that class or that room is no longer available. So up on the 3rd floor is where we'll have that. Lectures will go until about 6:30. So we're running out of time here. I got to pick up the pace, and then we'll have our lab time, and all of that is optional as we said. Okay. And labs are due by midnight on Friday. Homework is due by midnight every other Tuesday. Okay. Okay. Quizlet. helpful tool. You don't need it yet, but there's a class out there I've created, and I'll remind you of this. And it's helpful for just kind of drilling on stuff, especially before a midterm, something like that. Okay. There's what it looks like. You do not have to sign up. You can just kind of drop in and, follow the Quizlet set. Okay. But I'll remind you when we get there. Announcements in orange. Okay. So stuff like that comes at the beginning of lecture, and then review slides. So we'll go over a couple of things, especially on a Tuesday after a long weekend. Okay. And then we'll dive into our lectures, and then I will have you do some practice code. Okay. Solve some small problems, discuss the solution, and then we'll move on. Okay. So let's take a quick look at Program IZ real quick before we go, or before we move on. Programiz.com. We saw that. There's a Vimeo showcase here. If you need this, I usually have this for more of my beginning classes, but you can come back and watch these videos if you need a little guided tour through some of this stuff. They're pretty straightforward. I'm guessing most of you probably have this stuff figured out, but it's here in case you need it. And again, if you want to sign up for Pro, go ahead and start poking around there and let me know that you did, and I'll upgrade your account so you can have full access to that system. Okay. So your email will be private, and generally speaking, just don't put any other, private information in there, personally identifiable information. Okay. Now, when you get on to Program IZ Pro, I'll come back and remind you this, but remember to scroll all the way to the bottom. One of the things they haven't quite figured out, they're very much a content company, but at the bottom of the home page for your Pro account, and even though it says upgrade, it says that's to upgrade to full access. You're going to have a Pro account for free. And at the bottom, there's something called a playground. So these are large, programming environments with folders and data and code. Okay. So you can create these things, name them, and by default, you'll have 5, but you can create as many as you want once we upgrade your account. Okay. So I just wanted to show you where that is. Again, it's at the bottom. You got to scroll all the way to the bottom of that screen once you create an account. Okay. So if you want to jump into that anytime you can, but I'll come back and remind you of that when things start getting a bit more heavy. Okay. Yes.
So these are linked to our,
Sorry.
are these still like linked to our account?
These would be linked to your account. Yes. In order to see these, you would have to actually get an account, a free account. But yeah, once you do that, then they're stored in the cloud, and they're a lot more like normal documents. So the sharing part is not quite as confusing as we saw with the online compiler. Okay. And there's a lot less risk of losing work because, again, it's going to auto-save a lot like most of the systems that we actually use. So for the really big, gnarly assignments that we get to, I'll be recommending you kind of move away from the online compiler and work in a more dedicated system like this, either on your own, like VS Code, or something like Replit, or preferably Program IZ Pro, because we have such a good relationship with those folks. Okay, so lab 1, and then we'll get you out of here. So this is one of my favorite little problems that I find so annoying because it seems like it should be so simple. And there are many possible solutions to this, and I find it fascinating, and that's why I chose it for this year's lab 1. So I'm calling this recursive permutations. So here's the problem. We want to write a recursive function that prints every possible permutation of some array of characters. So remember, permutations, we're not allowed to reuse something, right? So we want to find all the different ways, kind of like dealing ourselves a deck of cards on the table, maybe 8 cards, and rearranging them in every possible combination. So there are a number of different ways to do this. Of course, we could use a library, but we're not going to do that for lab 1. One of the real good skill building approaches is recursion. Okay. So let's take a short string of 3 characters in a character array, size 3. So we would like to print out every possible permutation of that and print out how many of those we just printed out. Now, mathematically, we can go find the equation for permutations and know that that's going to be three things is going to give us six permutations. So you could calculate the count at any time, or you can do it, empirically, up to you. Okay. But those would be the answers. And then the blue number there at the end is how many things you just printed out. But we want to write this function so that it works for theoretically any size array. Of course, as the array gets bigger, your algorithm is going to be doing a lot more work recursively. Okay. So we're going to talk about this just in a second, but we're going to start with this prototype. So now in C++, if you recall, when somebody like me wants to give you some parameters, I give you a prototype for a function. So a prototype is not the function. It's like a little index in a book. It says, hey, you're going to go write this thing, and it's going to look like this. Now, you'll notice I put some question marks here at the end. You can expand these arguments as much as you want to solve the problem, or just work with those first two arguments. I'm pretty sure you're going to need some more arguments, but I would like you to otherwise follow this prototype. So you have an array of characters, and I'll show you the syntax for this here in just a second. And then an integer size, because arrays in C++ don't know how big they are. That's a problem. So we have to send in the array and the size of the array and any other information you would like to provide. So that's the prototype. So our code is going to look like this in main. So this is how we fill an array with three characters in the main scope, right? So our curly braces there in main are setting up some variables that are only known to main. So str is the name of an array, and you'll notice it matches the data type of my function call. So I'm going to do something like this: permute str, comma 3, comma, whatever else you want to send in, okay? So I'll leave that a blank for the moment. And it's going to do all the work. It should print out the permutations, and it should also print out how many permutations. Okay. So notice it's a void function. That means it doesn't return anything. So somewhere in the bowels of your recursion, when you get to the bottom, you're going to try to print out something. Okay. So this is, like I said, it's a little challenging. Don't worry if you don't get this. I'm going to be pretty flexible on the grading. I'm just looking for your best shot at this problem. So let's talk a little bit about the strategy for this, okay? So first off, remember in C++, arrays are passed by reference. That means that when you pass that little string array, str, into this function, it is called letters. But anything you change in letters will automatically change str out in main. So if you are working recursively and you're changing letters recursively, as we'll talk about in a minute, you kind of need to decide whether you need to undo that change at some other point in time. Or do you want to make a copy of letters inside of your permute function and send down a copy when you're doing the recursion? So I'll show you a picture here in just a second. But that's an important consideration, that character arrays are passed by reference. So you want to be aware you're dealing with like a live wire there. Okay. Now, unfortunately, also, you cannot print an array just by saying cout str, right? These kinds of collection of characters do not automatically know where they end when you give them to the cout command in C++. So you're going to, unfortunately, need to write a loop to actually do that. It's just a couple lines of code, so you'll be writing a for loop for that, okay? And again, you can add more arguments if you like. And we'll talk a little bit about that here in just a second. Okay, so these are some of the first things you probably want to remind yourself of. Okay, so let's talk about how we might approach this, and let's open this up for discussion. So we have this function that needs to call itself. It needs to take some information, maybe modify that information in its arguments, and pass down a copy or some version of that modification, and then do something. And it also needs a base case. How do we know when we're done? Well, maybe if we don't if the size of our array is 0, we're done, right? So we're going to need to reduce the size of our array as we get deeper and deeper into recursion. How do we know how deep we are into recursion? Maybe we need another variable for that, right? So there are a number of questions, and there's more than one way to do this, but I'll show you a little bit of a hint here on the next slide. But does anybody have any thoughts about this? Questions? Yes.
When you say we can't use libraries, does that include the standard library?
You can use standard library, but if you're using things like, combination generation, like, hey, give me all permutations of this thing, I would say that's probably not the right thing.
Okay,
But if you want to use a string library to like convert something and do some printing or things like that, that's okay.
okay.
That's okay. Yeah. We want to focus on the recursion part of the lesson and not burden you with other stuff. Yes.
Wait, do we go to the exercise 1?
So probably the easiest way to do this is go to Canvas and then go to Lab 1 in your assignments. So if you're on Canvas, you are on Canvas? Okay, yeah. So if you go to your assignments and then scroll to see all the labs and then go to Lab 1.
It's all the way down.
Yeah, I think it's down pretty far. Yeah. If you go to your modules, you should see it. You should see it up pretty high up on the screen. Let me see if I can get back here. Sorry. Give everybody. Hopefully nobody has seizures from this. So you'll notice that. Boy, it's all the way up here. There you go. So week 1 on Canvas. You see our lecture 1 PPTX, and then right below that it says lab 1 algorithm versus data structure. It's going to be called recursion and permutation, so it's a little bit out of date on this slide. Okay, so that's the one you want to click into.
Thank you.
Yep, absolutely. Okay, so other ideas about how to approach this? Anybody want to hazard a guess or thoughts? I promise I'll help you out here. I want to open it up for people if you have some thoughts.
I mean, adding extra parameters to kind of like remember state might be kind of helpful.
Excellent suggestion. Yeah, and feel free to be creative there, right? So what recursive level are we at, right? So if we wanted to know, am I at depth 0 or depth 1, then maybe I want to add an argument to that main section that starts out as a 0, right? And every time we make a recursive call deeper, we want to increment that value by 1, okay? So that might be one thing, right? So let's look at the tree, and some other things might come to mind here. So let's take a look at our recursive levels, and we need to get better at thinking this way. So I've got this string ABC, and I know it's got 3 numbers in it, and my goal is to produce this kind of output. So one way to think about this is to think, okay, I just was given this letters array, and I know it's got 3 things, and they go from 0 to 1 to 2. So over here, I can see I need to produce A and then all of the permutations of what else, right? So at level 0, one thing I could do is think, okay, well, I'm going to do the A words from level 0. And then once those are done, I will work on the B words from level 0. And then I will work on the C words from level 0. That's a loop, right? And inside of that loop, we're going to be calling the function with whatever letters we're not working with at that moment in time. So for example, if I'm working on the A, maybe we should make a copy of that array with just a B and a C in it and send that down to the next recursive level so that I've got an A, and then now the next level is dealing with a smaller problem, right? So level 0 has the A, and then level 1 is going to have a copy, a completely different string character array, not the same one necessarily. You might find a way to do it, but different one that's smaller. And now that orange array is still waiting up there at level 0. So remember, this is how recursion works. We don't lose level 0. It waits around and holds on to all of its data. So if I send down a copy, that copy lives and breathes at level 1. And we now have that same loop. So that's our recurrence. We're calling the same function. It's like, oh, you gave me letters with two things. Okay, I'll start a loop. And from inside of the loop, I'll remove a letter. Let's say we remove the B, and I pass down an even smaller solution, one character. That now we're at our base case. Or maybe we go one further and we have a 0 size, right? But either way, we've kind of reached the bottom, and that's our ABC permutation, okay? So the beautiful thing about recursion, if you remember, is when we unwind, this stuff goes away. We go back up to level 1, and we're still inside the loop with the blue array, okay? So that level has a different letters array than the level above. And the next thing that we're going to work on there is the C. So if we say, oh, okay, I'm going to pull the C out, make a green copy, and send it down this time with just the B. Now we're back down at level 2, and now we've got our A, C, B pattern, okay? So I'm not giving you all the answers here, but this is the primary pattern in which we probably will follow in order to explore all of the different permutations. A plus everything below that, and we just keep, slowly making the problem smaller and smaller. But we always got to come up for air, right? So we come up to this level, and we're done, right? We did the 0 and the 1 with the blue array. So we're done at level 1, but we've really only done the A at level 0. So the process continues. So the loop at level 0 goes to position 1, and the whole process starts again with the B. So it's, of course, symmetric because we're just calling the same code over and over again. So forgive my animations, they're not as fancy on this second round over here. But basically, we get our B, A, C, B, C, A. We unwind, go back up to the top, go to the C, okay? So in this class, we're going to use a lot of recursion. And part of the skill we have to develop, let me bring all this stuff onto the screen, is imagine an imaginary tree. It never all exists all at the same time. We really only create it one branch at a time, and then the branches go away as we unwind from recursion. But this is kind of the view that algorithms folks will start having in their heads. They'll say, okay, at one time or another, I'm going to travel down all of these branches, and that gives me an opportunity to explore every permutation of those letters. Now, how I get them printed out on the screen, you might find to be a little challenging. But if you can recursively do this kind of exploration, you've got your arms around a big piece of the course, okay? So there's more than one way to do this for sure, but I've kind of narrowed the boundaries a bit, so this might be the most straightforward approach. But if you find another one, just reach out to me. And if you get to a point where you just say, hey, professor, I really think I've found a different prototype for this function, I'd really rather do something different, then I will probably say, okay, please explain your strategy. But I do want to stay away from the string data type because we're going to be doing a lot with arrays in this course, okay? So that's our lab. That's due on Friday. And, again, don't let it knock you over if you don't get it all. It's kind of one of our more challenging labs out of the gates. The second lab this week will be quite a bit more easy, okay? And if it seems like everybody's struggling, I might put out some more hints out there. Feel free to talk amongst each other if you want to strategize and share some ideas. But that's all we got for you today. I'll let you guys go. And let me know if you have any questions. Otherwise, I'll see you on Thursday. Okay. Thank you.